Okay, everybody, this video is for topic part one, number one, electromagnetic waves. And what I'm going to do is I'm going to call up the summary notes. That's going to be our main source for this video. So let's just review this. Now, you guys talked about electric and magnetic fields in physics 2. So you may not have talked about electromagnetic waves. So I'm not going to talk a whole bunch about reviewing electric and magnetic fields and the so-called wave equations. Let me just assure you, you guys may have mentioned Maxwell's equations. If you remember Maxwell's equations, those are the collection of laws that deal with electric and magnetic fields. And there's Gauss's law for electricity, Gauss's law for magnetism, Faraday's law, and then the Ampere-Maxwell law. So the ones that are important to derive the so-called wave equations for the electromagnetic wave are Faraday's law and Ampere-Maxwell's law. And if you might recall that Faraday's law says that if there's a changing magnetic field in some region of space, there will be induced an electric field. The Ampere-Maxwell law says there are two sources of magnetic field: physical currents, flow of charge, and changing electric fields. So if in a region of space there's a changing electric field, there's going to be induced a magnetic field. It's the induction of the electric and magnetic fields from changing magnetic and electric fields that are important for this concept of the electromagnetic wave. And that was one of the really neat things that Maxwell was able to show. So you can take the Faraday's law and the Ampere-Maxwell law, and you can combine them to get two differential equations, one for the electric field and one for the magnetic field. Now, to do this derivation, it does take some vector calculus. So I normally don't even do this if we're meeting in a regular semester. The derivation, it's a nice derivation, a nice application of some Calc 3 stuff, and we do it in Physics 415, optics. So if you're interested in it, take optics. But what you can do, starting with a particular geometry, and the geometry we're going to start with is, let me scroll down, I'll show you a picture. Let's assume that we just have an electric field that starts in the y direction. You can see this set of axes. X is going this way, y is vertical, z is coming out of the page and into the page. So if we start assuming an electric field in the y direction and that it's changing, you can actually get this differential equation for the electric field. Now realize the electric field in this case would be a function of x and t. So we're assuming that the field can have different values along the x-axis at different times, but it's always in the y direction. With those assumptions and Maxwell's equations, you can get this differential equation. Similarly, you can get an equation for the magnetic field, and you can show using the vector calculus and Faraday's law that the magnetic field would always be along the z-axis. That would be its vector direction. And it can have different values along the x-axis at different times. So B would be a function of x and t. Well, it turns out you get two identical differential equations for those fields. Epsilon and mu, you might recall from Physics 2, that's the electrical permittivity and the magnetic permeability of the respective medium. Okay, now, it turns out that these differential equations have the form of what we call wave equations. These are recognized partial differential equations in physics for waves. So like if you set up a wave on a string and analyze the displacement of a point on the string as a function of position along the string, which we'll call x, and time t, you would get a similar differential equation. And now you wouldn't get the permittivity and the permeability. For the string, you would have a term involving the tension in the string and the linear mass density. but the form of the differential equation would be the same, except for these constants. The epsilon mu would be different. So any wave, in fact, any wave will satisfy a differential equation of this form where you have constants multiplying the time derivative. So we call that a wave equation. And possible solutions of this wave equation, there are in fact a lot of different possible solutions, but we're interested in what are called the harmonic solutions, where you can the function e and b would be a sine or a cosine. So in fact, the solution of these differential equations, two possible solutions for the electric field, would be either using a cosine or a sine function, and similarly for the magnetic field. So if you go with the cosine for E, you're going to have to go with the cosine for B, assuming that the phi is the same. Okay, so these are the functional forms, the harmonic wave forms. All right, now, the focus here is let's identify what all these things are in these functional forms. I'm not going to have you guys manipulating these cosine and sine functions, really, but we do need to recognize what these physical constants are. So E sub m, that's the amplitude of the wave. That's how big the wave can be at a particular point, the biggest it can be, plus or minus. But we write that as a positive amplitude. And remember, units for electric field, SI units would be volts per meter. B sub m would be the corresponding magnetic field amplitude. What's the biggest the magnetic field can be? SI units Tesla. K, right here, we call that the angular wave number. And it would have units of angle per length. So SI would be radians per meter. We'll relate that to something called the wavelength in just a few seconds, okay? Omega is the angular frequency in radians per second. And then the phi, that we call just a generic phase angle. And that would be a constant value. And the choice of that phi often is 0. But if you chose some other phi, all that's going to do is shift your cosine or sine function, okay, shift it along the x-axis at a given time t. So it's really a degree of freedom that we have to describe a wave, but often we don't have to worry about the value of phi. Okay, we'll just set it to 0. Okay, now let's delve into more of what the wave looks like, and also more into this angular wave number and the angular frequency. So here is a generic picture of what a harmonic electromagnetic wave would look like. This one, it's traveling in the plus x direction, and we've taken a snapshot of it. So if you look at this purple wave, that looks like harmonic, right? Cosine or sine. That's the electric field wave. Notice that it's only along the y-axis. Now, that is a restriction. An electromagnetic wave may not have the electric field always along a certain axis. This thing could spiral as it travels. We'll talk more about that when we talk about polarization. What the electric field axis is doing in time determines the polarization state. For right now, we're going to look at what's called linearly polarized electromagnetic waves. So the electric field is always along the y-axis. The magnetic field is always along the z-axis, if this is traveling along the x-axis. But there's that purple sine or cosine. Locked in step with that harmonic wave, you have this orange or yellow magnetic field. Notice that when the electric field peaks, the magnetic field peaks, right? Okay, so that's what a typical electromagnetic wave would look like. Now, if you notice, I have an oscillating charge here because we all remember from physics too that the source of electric and magnetic fields, right, is either charge or changing electric and magnetic fields. So in this case, I have an actual physical charge. Maybe it's an electron that's oscillating up and down, generating this electromagnetic wave. Okay, what I want you guys to focus on, this is a snapshot at time t. There is a distance between what we'll call crests. If I go from one crest to the next crest, that portion of that harmonic wave just repeats, right? So the distance from crest to crest, we call the wavelength. Now that's also, you could define that as the distance from trough to trough, or the distance from one point to the next point after one complete cycle. But I think it's easiest, for me at least, to visualize the distance from crest to crest. So that's what we call the wavelength. Also realize that if this was a video, right, and we let this go in time, what's going to happen is that this electric field, which is, it's right here at this time, right? What this electric field vector is going to do is go down and up. Sorry, that's not perfectly vertical, but that's just going to be going down and up, right? Up, down, up, down, up, down. One complete cycle would be from maximum up, down to maximum down, back up to maximum up. That would be one cycle. And the time for that would be one period. That turns out also to be the distance, the time for this wave to travel one wavelength. Okay, now let's quantify or let's give names to these quantities that I'm discussing. Okay, so we talked about the wavelength, and we conventionally use the Greek lambda. Okay, the angular wave number k is related to the wavelength through this relationship. K is 2 pi over lambda. So just remember that. Okay. Oh, also a word about k. Officially, it's the angular wave number. The wave number with no angular in front means 1 over the wavelength. So the reciprocal of the wavelength is sometimes called the wave number. But most people don't really care about the wave number, except like crystallographers. So if you hear me say wave number, I always mean the angular wave number, 2 pi over lambda. Okay? All right. We talked about the time for one cycle. That's the period, capital T. You guys are used to the period from circular motion, and possibly talked about wave motion before. The reciprocal of the period is the frequency, the number of cycles per time. If we're using seconds for the period, then the frequency would be cycles per second, which we call, right, hertz. And then the angular frequency, omega, just like in circular motion, is related to the frequency in the period, 2 pi over the period, 2 pi times the frequency. Okay? Again, you guys know that from circular motion. Let's do some more housekeeping. Oh, the plus minus sign between the kx and the omega t. If you go back up here, right, I said a solution, you could have a plus or minus here, and it's nice to have that freedom because physically, a plus sign means that would be a wave traveling to what we would call the right, increasing x, towards more positive x. I got that wrong. So, I'm so sorry. A plus sign would be traveling to the left. A minus sign would be traveling to the right. It's opposite of what you first might think, okay? Don't worry too much about that. I just say that in passing, but we're not going to really do anything mathematically with that plus or minus sign. But plus means going to decreasing x, and minus would be towards increasing x. Okay. And then the phi we talked about. You can throw that in there if you want to match some initial condition, for instance. I don't think we're ever going to have to worry about the phi. Okay? All right. Now, the speed of a harmonic wave. And again, this is for all harmonic waves, for all types of waves, sound waves, water waves, waves on a string. The speed turns out to be omega over k, or wavelength times frequency. Okay? Always. All right, so V equals lambda F or omega over K. Now, for the electromagnetic wave, we have an additional relationships. The ratio of the electric field to the magnetic field is also going to give you the speed. So if you take the amplitude of V over the amplitude of B, you'll get the speed. But you can take the ratio of E over B at any time, at any position, and you'll always get V. Okay? The only time that's not true mathematically would be when both of them are zero, right? Because there is a time in, there is a position X, like right here, you guys see right here, for instance, where both those fields are zero at that moment in time. So that wouldn't work, but that's the only exception. Also, the speed is 1 over the square root of the permittivity times the permeability. That comes mathematically from the form of the differential equation. The speed of the harmonic wave is always going to be 1 over the square root of that factor, multiplying the time derivative. Okay? All right, so we have that relationship also for the speed. Okay, now, if we look at free space, vacuum, okay, so we can't have any charge or matter in vacuum. The fact that there's no charge, that's why it's free. Haha, joke number 1 of the semester. No charge, it's free. Okay, I'm sorry. But we can't have electric and magnetic fields, okay, in free space. So in free space, we're going to put epsilon naught and mu naught, right? That's the permittivity and permeability of free space. You guys might remember, right? Let me see if I can do this off the top of my head. Epsilon naught, 8.85 times 10 to the minus 12. Yes? And mu naught, 4 pi times 10 to the minus 7 in SI units. Okay. If you put those numbers in there, take the square root, take the reciprocal, you get this nice universal constant. It's 2.99, but we often just round it up to 3. 3 times 10 to the 8 meters per second. We give that a special symbol, little c. That is the speed of light in free space. And as far as we know, this is the fastest that anything in the physical universe can travel, and only light can do this, pure energy, in vacuum. Okay? So light, electromagnetic wave, sometimes you'll hear me call it electromagnetic radiation or light. The fastest it's going to travel is in free space. That's its speed c. In any other medium, it's going to travel at a slower speed. Now, to give us an easy way to get the speed, at least in a formula, somebody said, well then let's write the speed of light in some medium as c, the speed in free space, over some constant of the medium. This constant we call the refractive index, or the index of refraction, n. It is a pure number, and what is the smallest it can be? Well, the fastest that v can be would be c in vacuum, so that corresponds to a value of 1 for free space. And in any other medium, v is going to be less than c, so n is going to be bigger than 1. So for any other medium, n is going to be greater than 1. Okay? Air's index. You'll see a lot when we do examples or homework tests. We'll assume that air's index is approximately 1. It's slightly bigger than 1. It's like 1.0004, blah, blah, blah. And sometimes that's an important difference, that it's not exactly 1. But most of the time, we're going to assume, it's close enough to 1. Okay. Another thing that you should know, and I'm throwing this out here without proof, if you look at the intensity carried by an electromagnetic wave in vacuum, remember, intensity is power per area, right? So power, SI units of watts, area, meters squared. So, for instance, imagine you have a sunlight shining, right? It's traveling in space. If I put a square meter, right, of a screen there, and the sun hits that, how much energy per time is hitting that square meter? How much power is being delivered by that wave, right, on that square meter? So that's what we call the intensity. And the intensity actually fluctuates in time, right? Because if you look at the electromagnetic wave, remember the energy stored in the electric and magnetic fields, well, there are some points where the field's really big, like here, and then some points where the field vanishes. So the intensity is not a constant spatially or in time. However, these frequencies are so high usually, right? And these speeds are so fast that that fluctuation is not usually noticed, okay? In fact, I would say almost never noticed unless you're looking at extremely short time scales. So the average intensity is what we're always interested in. And the average intensity, there's a formula. I'm not going to do the derivation of that. Again, it requires some, a little bit of vector calculus. Okay, so We do that in optics. But I do want you guys to see that the average intensity, it's nice to remember that it's proportional to the square of the electric field and the square of the magnetic field. Okay? All right, now, the electromagnetic spectrum, I don't want to spend a tremendous amount of time on. Well, you know what? In fact, what I'm going to do, I'll tell you what. I'm going to stop this video now because I don't want to make it too long. I'll make another video where we continue and talk about the electromagnetic spectrum and light in different media. So I'm going to end this here. All right, and then I'll make another video. Goodbye.